Next problem talks about a truck that's going across a bridge. And the question here is how much normal force is there being applied by this side of the bridge and this side of the bridge when the truck actually makes it onto the bridge. Now at this point we're going to say that the truck is right at the center. So if we have the truck right at the center, then we know what distance it's going to be. We know its lever arm. All right, so the distance of the entire bridge, we'll just call that L, and then we use the first condition of equilibrium in order to figure out what relationship there is between all of these forces. So let's say we know the weight of the truck, we know the weight of the bridge. How do we figure out the normal force 1, normal force 2? All right, so net force is going to be equal to 0. So basically summation of forces, the bridge and the weight of the bridge and the truck are both downward. The normal forces are they're both upward. So we get this equation right here. And we get the 2 upward forces are going to be equal to 2 downward forces. That's pretty easy, pretty straightforward. Second condition of equilibrium says the net torque is going to be equal to 0. So this one identifies the pivot point right here at N2. You don't have to do that. You can actually identify your pivot point at N1. Now, why would we identify it at N1? Why not like at the middle of the bridge? Why would we choose one of those two? Okay, so when you identify where your pivot point is, remember that in order to produce torque, you have to have a radial arm. You got to have a distance from that pivot point. So if you identify your pivot point at a force that you don't know, then when you figure out the torque of that force that you don't know is going to be multiplied by 0 because the distance is going to be 0. So in these scenarios, it's pretty convenient when you don't want it to rotate to set your pivot point at a location of unknowns, because that means the torque that's going to be produced is going to be 0 for those. All right, so with that being said, then that means normal force 1, that's going to produce a clockwise torque, so that's going to be a negative N1 times L. And then the 2 weights of the truck and the bridge are going to be positive torque because it's going to be a counterclockwise torque. And it's going to be half the length of the bridge. All right, so net torque is going to be equal to 0. The weight of the bridge times half the length, and then the weight of the truck times half the length, and then we subtract the normal force times its full length, and that's going to be equal to 0. So to solve for the normal force, it's going to be equal to basically all those weights, the weight of the bridge, L over 2, plus the weight of the truck, L over 2, and then we divide by L. That actually will get rid of the L, the length of the bridge. It doesn't even matter. So basically, it's going to be the 2 trucks added together. It's holding up half of the total weight, the truck and the bridge added together. And then after you have the normal force of 1, all right, which is this force right here, you can plug that back into the first condition of equilibrium and then figure out that the normal force 2 is going to be the other half. So the normal force 1 is half the weight of the bridge and the truck together, and then the normal force 2 is the other half. So let's do the same thing, except this time we're going to move where the truck is. The truck is not going to be where the center of mass of the bridge is. It's actually going to be a little bit over, about 1/4 from the right-hand side. Okay, so first condition of equilibrium, net force is going to be equal to 0. So again, all the upward force is going to be equal to all the downward force. So normal force 1, normal force 2 are going to be equal to the weight of the bridge, weight of the truck. All right, nothing changes there. Now what does change a little bit with net torque be equal to 0, we put that pivot point back at N2, is that we have a little bit difference now. Right, we got a little bit difference as far as the distance of the truck. So with the pivot point being here, instead of the truck being 1/2 the length of the bridge, is now 1/4 the length of the bridge. All right, so when we isolate and solve for N1, we take those the N1 L to the other side, we divide by L, and now we have N1 is going to be equal to half of the weight of the bridge plus only 1/4 of the weight of the truck. All right, so way over here, it only feels 1/4 of the weight of the truck. All right, so just a time of confession for you. When I was moving into our new house after just getting married to my wife, we were carrying an entertainment center, and the entertainment center had one side with a bunch of drawers, and then the other side of the entertainment center had a big hole in it for where the TV was going to go. And I may or may not have taken the one with the side of where the hole was for the TV. My wife thinking that, well, you get on one end, you're going to have half the weight. You get on the other end, you're going to have the other half. But in fact, since like this example right here with the truck being closer to the pivot point, then that means more of the weight is actually going to be distributed over here, and there's going to be, this side is going to actually feel less weight. So I confess that I accidentally, or maybe on purpose, made my wife carry a little bit more weight than me. Anyway, so N2 is going to be the other half of the bridge. So the half of the bridge is being supported by N1, the other half of the bridge is being supported by N2. And then N1 is only supporting 1/4 of the truck's weight. That means N2 has got to be the other 3/4 of the truck's weight by using the first condition of equilibrium. All right, so two forces are applied to the doorknob perpendicular to the door. The first force is twice as large as the second force. The ratio of the torque of the first to the second is what? Take a second to figure this out. All right, so what changes here? Well, both of them are being applied to the doorknob. That means that the distance doesn't change. Both of them are perpendicular. That doesn't change. It says the first force is twice as large as the second force. So the first to the second, twice as large of a force means twice as much torque. So it should be 2 to 1. So C is going to be the correct answer here. All right, so here we have a sign that's going to be hanging off the edge of a rod, and then we have this this cable right here. So the sign hanging from the rod is attached to the wall, and then the cable goes up to add additional support. All right, so to look at the forces that are acting on it, we got the rod that's holding up the sign. All right, so that's going to apply a force there, and then you have the sign itself that applies a force downward. Then you've got the tension of the cable that's going to apply a force. Now, if you think that these are all the forces, you got to be careful because there are forces over here on the wall as well. Okay, so what direction does the force at the wall apply? What direction does the force at the wall apply? Well, think about this. If I set my pivot point right here at the very end, then the only force that's going to be producing torque would be the weight of the board, which means it would rotate counterclockwise. So that means that the pivot point over here, this fulcrum, is actually pushing up. It's applying an upward force. Okay. Also, if I look at the net force in the horizontal direction, the weight of the board itself and the weight of the sign do not supply a horizontal torque. A horizontal force. And this tension only supplies an upward and a force to the left. So if I didn't have a force to the right supplied by this pivot point over here, then that means that I would just have that tension that would be pushing the sign into the wall without the wall pushing back out. All right, so this point right here actually supplies two forces effectively, one that's pushing out from the wall and one that's up. All right, so what are each one of these forces? Let's suppose I know the weight of the board that's holding up the sign, and let's say I know the weight of the sign as well. So what's going to be the amount of tension that's being applied? Let's say we know the angle as well. All right, so here's our free body diagram that kind of shows, you'll notice our free body diagram actually is not a dot anymore. It's not a point. It's actually almost similar to what the object looks like itself. All right, so we kind of expanded out a little bit. So the weight of the board is here at the center. The weight of the sign is all the way at the end. That's a full length of L. The tension's being supplied over here, but you'll notice they identified D. If we extend the tension out, the shortest distance between that line and the pivot point is going to be D, and that's going to be L sine of theta. That's the opposite here, sine of theta. All right, so that's our lever arm. D is our lever arm, which if you use the torque equation, you get tension times L times sine of theta. That equation would give it to you anyway. All right, so let's figure out what each one of these forces are. Let's start with the force of tension, right? So the tension in the cable, well, what can we use? There's several things that we can use for this. We can use net force in the horizontal direction, net force in the vertical direction, but the problem with that, the net force in the horizontal direction, is that we have this N that we don't know, as well as that horizontal force of tension. So that's two unknowns that we would have in that equation. If we look in the net force in the vertical direction, then we got this F that's pushing up on it and tension that's pushing up on it. Those are two unknowns as well. And that would actually give me a total with those two equations, that would give me three unknowns, so that's not enough. So we're going to look at net torque going to be equal to 0. All right, so let's kind of work through those two equations I just mentioned with the first condition of equilibrium. So that means the normal force minus the cosine component of tension is going to be equal to 0. For the y direction, the force upward and the sine component of tension is going to be equal to the force of gravity of both the board and the sine. And then if you look at the second condition of equilibrium, where we set the pivot point right here at A, which remember we could set it anywhere we want, but A is going to be really convenient because that gets rid of both F and N. It gets rid of F and N because both of those have a distance of 0 with respect to that pivot point. So that means that the weight of the board at half L, that's going to be one torque. Weight of the sine at times L, that's going to be another torque. And both of those are going to be negative, while the tension, the sine component of tension, is going to be positive. Okay, so in solving for this, you can see that the two negatives, we can take that to the other side. L is going to cancel from all of this, and we divide by sine of theta. That will actually give me the tension. Is going to be equal to the weight of the board divided by 2 plus the weight of the sine, and then we divide by sine of the angle, and that gives us the amount of tension in the cable. Now, what's the purpose of this? Why we even care? Well, if you are designing this, you want to know how much tension there's going to be in that cable so that you can know how much strength you need in order to actually affix it to the wall. All right, so let's take the same condition, the same scenario, except we're going to add a little bit of complexity to it. All right, the sine is gone, and instead of having a sine there, we're going to have a student running out onto this board. Okay, so the question is, how far can that student go before the rope breaks? Before the rope breaks. So how far can that student go? What's the distance d before that cable breaks? Well, first of all, we need to know how much force it takes to make that cable break. But let's call that tension max. All right, the maximum amount of tension, and then use that to find the distance that the student could walk out before that tension breaks. All right, so how far can the student walk before the cable breaks? All right, so looking at all the forces that are acting on our board, right? We got the weight of the student times d, whatever that is. That's going to be his torque, and then the weight of the board times half L, and then the tension of the cable is going to be the sine component of that, and then we're going to set the pivot point right here at the origin again. So using the second condition of equilibrium, net torque is going to be equal to 0. So that means that the tension L sine of theta, that sine component of tension, times L out here. That's going to be positive. It's going to produce a counterclockwise rotation. And then the student as well as the board are both producing a clockwise rotation. So the student is distance d away, and the board is half of L. Half of L for its center of mass. All right. So we rearrange this equation, and you can see that we take the student. That's going to be positive, so we take that to the other side, and we divide by the weight of the student. 2 is going to come in because basically you're getting common denominator. You're going to get the weight of the board, so minus the weight of the board times L divided by 2, and then we're going to get a common denominator, so we're going to multiply by 2 and then divide by 2 here as well. So that's going to be the distance that the student can go before the cable is going to break when you plug in those numbers. So this next example, we're going to talk about tilting a box. So we consider a box that's 27 kilograms, has a height of 1.1 meters and a length of 0.8 meters. A force is applied to the horizontal upper edge. So we apply a force on that upper edge. We've got the normal force that's pointing up. We've got the force of gravity that's pulling down. We've got a force of friction that is opposing the direction that it's trying to slide. All right, so we've got all these forces that are acting on it. So what's the minimum force required? How much force do I need to apply up here at the corner in order to get it to start to slide, or not start sliding, but actually start to tip, so to tip over? How much force needs to be applied? All right, so let's start going through the forces a little bit. If we look at all the forces that are being applied in the corner, all right, all the forces that are being applied in this corner right here, those forces are going to be, you got the upward force of normal force. because when you actually start to tilt it up, when you start tilting it up, all that normal force is going to be applied at the very end, that very tip right there on the side. Okay, the force of gravity is still going to be down from the center. The force of friction is actually going to be at that point as well. So that pivot point right there, that pivot point is going to have the normal force and the force of friction being applied there. So if our normal force and force of friction are being applied there, and we consider that the pivot point, then those two are not going to produce any torque. So no friction torque, no normal force torque. We're going to have a force of gravity, and we're going to have the box itself as I'm applying a force. That's going to apply a torque as well. All right, so if we look at our forces that are being applied, we have the force F that's being applied at 1.1 meters above where that pivot point is. And then we have this force of gravity that's being applied not at the end, but in the middle, halfway of that 0.8. So 0.4 is going to be the lever arm for the force of gravity. All right. Now, the force of gravity is actually at the center right here. All right. So that's the point where the center of gravity, if you look at the box. But if we extend the line down, and then we have the shortest distance from that pivot point to where the force is being applied, then that gives us our lever arm. So that's much easier. So rather than taking that midpoint that's up here for the force of for the center of gravity for the object, and then trying to figure out the distance to that, and then using triangles and angles, it just gets all complicated in order to try to get that angle in order to use force times distance times the radius times the sine of the angle. We can just use that lever arm right there if we extend that line through. It makes the math easier, right? Okay, so only two torques are being applied. Only two torques, the force of gravity and that force. Now this force here is providing a torque that is going to be, if you look at it, it's going to be clockwise. Yeah, it's going to be a clockwise torque. So that's going to be a clockwise torque, and this one's going to be a counterclockwise torque. So basically they're going to be, we know that this force right here, its torque has to be greater than the torque provided by the force of gravity. Okay, so we set that where that torque provided by the force, so it's force times R1, is going to be greater than or equal to the mass times gravity, the force of gravity times its lever arm as well, half of the distance of that side. All right, so if we solve this, we get 27 times 9.8, that's the force of gravity, times its lever arm, which is 0.4, we get 105.84, divided by 1.1, and we get that the force has to be applied at least 96.2 newtons in order to get it to start tipping over. The next question is, what's the minimum coefficient of static friction required for the block to tip with an application of the force of this magnitude? So how much, what's the coefficient needed? Well, in order to figure out coefficient of friction, I need to know two things. I need to know the amount of friction, and I need to know the normal force, the amount of friction and the normal force. Okay, so looking at our free body diagram, the four forces that we have, we got force of friction pointing to the left, that force that we're applying to the right, normal force up, force of gravity down. So this actually becomes a relatively easy scenario to do because we already figured out what that F needs to be on the previous slide. We figured out that it needs to be 96.2 newtons. So that's going to be equal to the force of friction. That's going to be equal to the force of friction. Force of friction has to at least balance that, because if I'm applying more forward force than backward force, then the force of friction is not going to prevent it from sliding. So the force of friction needs to be at least 96.2 newtons. Okay, the normal force, the only two forces in the vertical direction, normal force is equal to force of gravity, so it's going to be equal to 27 times 9.8, which is 264.6. And then, of course, the force of friction has to be greater than that force. So the minimum force of friction is going to be equal to that force F value. So the coefficient of static friction times normal force is going to be, it's got to be greater than that force in order to prevent it from sliding. So you plug in your force, which is 96.2, divided by 264.6, which was the normal force, and we get the coefficient of friction has to be at least equal to greater than 0.364 in order to prevent it from sliding.